Good morning. We're going to talk about the design and performance of combined basic devices to control undesirable bridge deck displacement and damage during major earthquakes. The outline includes an overview, a description of the influence of Wisner earthquake on Manabí bridges, basic criteria employed in the design of control components of non-isolated segments of Los Caras Bridge, which is going to be used as an example. Design and performance of neoprene longitudinal shock absorbers, design and performance of transverse concrete shear keys, design and performance of vertical steel bar anchors, and some conclusions. This paper describes criteria employed in the design of neoprene shock absorbers, concrete shear keys, and vertical steel bar anchors, which are the three kinds of devices employed to control large displacement in bridges and huge damage. But we will focus on certain construction details because they prove it to be very important on the overall system performance. We assessed the performance of this design under the April 16, 2016 7.8 magnitude Wisner earthquake in Manabí. Displacement control of shear keys and bridge deck displacement in other bridges of Manabí were also studied for comparison purposes. After the earthquake, general details and design criteria proposed. Improved design criteria and details for concrete shear keys and steel bar anchors based on actual seismic performance are also presented. Major earthquakes produce large horizontal, large vertical ground accelerations, which leads to large horizontal and large vertical displacements in all components of the bridge. Bridge deck and substructure superstructure connection elements require a special design and construction detailing to control damage and permanent displacements, particularly when using neoprene pad bearings, which is the most used in Ecuador. Most bridges in Manabí had only shear keys to control displacement, lateral displacement. Only accesses of Los Caras Bridge were designed and built with 3 displacement control systems. But there was another aspect important. Seismic reduction factor was much smaller in Los Caras Bridge than it was used in conventional ASTO standard design. We accepted only up to 1.25 reduction factor for earthquake stresses. On April 16, 2016, a major earthquake occurred between the provinces of Manabí and Esmeraldas. An estimated peak ground acceleration in Los Caras Bridge was 0.9 Gs. Here is a map showing Pedernales, very close to the epicenter, with 1.41 peak ground peak ground acceleration. Here is Manta with 0.52 peak ground G's peak ground acceleration, and here is Bahia with Los Caras Bridge, approximately 0.9 G peak ground acceleration. This is the a general view of a plan view of Los Caras Bridge. It has a central section, which is an isolated section, and 2 curved accesses without isolators, which needed to control those large displacement and low high damage. And the bridge extremity needed to be designed to have a performance compatible to the isolated segment of the bridge. That was the idea. Again, the reduction factor for seismic actions was up to 1.25, which is rather low. In addition, 3 complementary components were included. I'm going to talk about all of them. The idea behind the use of those 3 elements longitudinal shock absorbers, shear keys, and vertical anchor bars was not to eliminate damage, but to focus such damage in certain components that could not compromise general structure. Their use allowed for continuous functionality both in isolated and non-isolated segments. The design allowed some minor damage in compression neoprene plates. It allowed also limited damage in reinforced concrete shear keys for transverse displacement. Vertical anchors were designed originally to restrict vertical displacement, but they have shown an additional beneficious behavior, which is when the bridge deck has lateral displacement as shown in this graph, there is a component in the transverse direction, which is a restitution force. It allows, in most cases, that the structure after this kind of deformation returns to its original position. Longitudinal shock absorbers were included in design and construction to control damage in standard structural elements. They were located inside expansion joints. Here is one of the curved axes, and those are the expansion joints, and inside the expansion joints neoprene shock absorbers were located. No damage was observed in neoprene longitudinal shock absorbers after the Wisner earthquake, but when checking all other bridge components, some neoprene bearings just below the neoprene shock absorber in San Vicente abutment reached an inelastic range. There were traces of overheating. The darker areas here correspond to overheating or almost revulcanizing process. What was interesting is that it doesn't matter that there was high temperature here, the whole structure returned to its original position. So it was a problem, but it was not a big problem. A combination of longitudinal and transverse deck lateral displacement was responsible for such behavior. When talking about shear keys for lateral displacement, this was the displacement control system most used in Manabí, in the analyzed bridges. Although a few bridges didn't even have this kind of device. Shear keys are reinforced concrete blocks located at a specific distance from the deck, a gap, which under seismic action work as transverse displacement limiting devices. That's a limit. Here you have shear keys in Los Caras Bridge. When designing, we found that we needed 3.5 centimeters gap in Bahia axis and 5 centimeter gap in San Vicente axis. But there was a different kind of behavior in both axes. In Bahia, where the gap was okay, the shear keys worked in an inelastic range, producing as part of such situation diagonal shear cracks. But in two piers in San Vicente, one of them exactly under the abutment of San Vicente axis, neoprene pads shown an overheating, which is the darker areas, almost a revulcanizing. Why? Because there was an increase in gap due to an original misalignment during construction. What was important is that no traces of neoprene overheating were observed in Bahia axis, and no visible cracking was observed in San Vicente shear keys, which means that both components act together when standing lateral displacement. There is one of the ways to withstand earthquakes is better than the other. Here we have such a description in a graphical way. First, when we have lateral displacements, only the neoprene pad works with a certain stiffness, and when touching the shear keys, there is a second component which increases the stiffness of the whole system. But when there is a larger gap, there is a neoprene overheating in this area. Several lessons were learned. The direction of cracks means that we need diagonal bars, diagonal reinforcement, not only when repairing the bridge shear keys, but when designing the bridge shear keys. It is very important. When the main direction of deck displacement was transverse and the ground peak acceleration was about 0.3 Gs, either large displacement, permanent displacement, or significant damage occurred in the shear keys. We see that here and here. Steel bar anchors originally are designed and built to control possible vertical upward movement, but they have the additional benefit when creating a restitution force. Most bridges in Manabí had only shear keys as a mechanism to control displacement. Only the accesses of Los Caras Bridge were designed and built with 3 displacement control systems. Seismic reduction factor was much smaller than what is used in a conventional ASTO design. Conclusions. The performance of the Los Caras Bridge during the 2016 Wisner earthquake demonstrated the successful coordinated use of the 3 types of damage and displacement control system together with the neoprene pads. They were analyzed independently during design, but from a performance point of view, they work together. They work as a system. A small variation in the dimension of gaps among elements is sometimes generated during construction can change the performance. We have to take care of that. It is advisable to control the elastic behavior of neoprene bearings, while shear keys can be designed to work inelastically. Bridge without an adequate design of shear keys, without neoprene shock absorbers, and without vertical steel anchors can have serious permanent lateral displacement and damage. Vertical anchorage bar are imperative to minimize damage in superstructure, but vertical steel bar anchors resist also lateral displacement. An optimal integrated design for the control of damage and irrecoverable displacement in the longitudinal direction of the bridge is achieved with small gaps between deck and shear keys. Contact between contiguous segments of bridge deck should have neoprene plates as transition elements. Anchor steel bars provide uplift control and lateral restitution force. Thank you. Any questions to this email address?